G'day, I'm Alister Christie from LearnDelphi.tv. I've been producing videos on Delphi since 2006 and I have a huge collection of tutorials, both free and paid. You can find out more by going to LearnDelphi.tv. This video is an extremely deep dive into a very specific topic. We're going to look at how hashing works in Tdictionary and how we can subvert it to our own means. Generics allow you to treat types like variables, so that you can write a piece of code with a placeholder type, then reuse that code with various different types. Here we have written a simple function that checks if an item is in a given array. We can then reuse that function, inserting different types, shown here with integers, chars, and strings. Rather than write your own collections, you get a bunch of ready-made containers that you can start using right away, available in the system.generics.collections unit. In fact, you don't need to understand much about generics to take advantage of the library. Just a basic knowledge of the syntax will get you started. The Tdictionary class, available in the aforementioned collections unit, is an implementation of a hash table. I remember having to write a hash table in my university days for some assessment or another. They're not particularly difficult to implement, but very easy to get wrong. The idea behind a hash table is that you are storing key value pairs. The key is unique and used to store or retrieve a value from the dictionary. The big advantage of hash tables is their speed. For the most part, it takes a constant amount of time to add a value and a constant amount of time to retrieve it. Contrast this with a sorted array, for instance, which will take you order n to insert and order log n to retrieve, where n is the size of the list, and this probably won't mean anything to you unless you know about big O notation, which is not as exciting as it sounds. This constant time behavior revolves around the hash function. The hash function takes the key and produces a quasi-unique value called the hash. In Delphi, we actually have a series of these hash functions which take values of various types and convert them to a 32-bit integer, and this integer is used to index into the array that is used internally within Tdictionary. In this video, we're going to cover a number of examples, starting with some introductory stuff, before we get stuck in and look at altering the hashing behavior. So this video is all about the code. So for our first project, we'll create a new console application. None of this newfangled multi-device applications. And we'll need to include the system generics.collections unit. And I'll also go to an all code layout and use a new keyboard shortcut, Control numeric plus, to increase the font size. That's probably plenty big enough. So I'll take that out. Finally, we'll need a variable. Of Tdictionary, and we'll map a string to a string for now. Let's clear that. We want to create our dictionary, which is probably most easily done with a bit of copy and paste. There's on the create constructor, there is quite a variety of parameters. We will be looking at some of them shortly, but for now we won't worry at all. And of course, we will need a free. Now let's start with something quite simple. Oops. Okay, halfway through the week. And we'll just write out and we'll use the items property. There's a bunch of different ways of adding. Typically add or which will throw an exception if you are adding something that's already present, or add or set value, which will add it or update the value based on the key. Okay, now before I go running that, if I not control click on that, but if let's go to Tdictionary and scroll down and have a look at the items property, we'll see that it's the default value, which effectively means we can omit it. So we can just say that. And if we run our application, if you saw that briefly, it should say, tell me why I don't like these. So that's a pretty basic usage of Tdictionary. So let's have a look in quite a bit more detail how add is working. If our dictionary is, or the internal array in our dictionary is getting too full, and that point is 75%, we double the size of the internal array. So just quickly control click on that. So basically we're doubling the capacity and then rehashing everything. So everything has to be re-added back into the new array. We calculate the hash code based on the key. We then calculate an index, so we go and do a little bit of a search for an empty slot, and if we find our item already there, we raise an exception, duplicated item exception, and if not, if we find an appropriate slot to put it in, we call doAdd, and we add to the internal array, which is a T-item array, which is an array of T-item, and T-item is the hash code that we've just calculated, the key and value, which is what we're particularly interested in. And then we increase the count, and there's a couple of events that get fired. Now, what we are particularly interested in this video is how this hashing works. So let's control click on the hash function, and the interesting bit of this is this GetHashCode on fcomparer, and if I control click on that, we see that it's an I-equality comparer, and we have this GetHashCode function and an equals function, which we will come back to a bit later. So if we go find where f-equality, so that our fcomparer is assigned, we see that it occurs here in the constructor. The constructor we call is this this create here, which passes in nil. So our fcomparer is nil, and we get assigned this default function in T-equality comparer. So if we have a look at that, we'll see that it's basically doing some magic code, which goes and sees if there is a appropriate I-comparer for the given type we've passed in, and in the case of string it does. In fact, I think in pretty much all cases it will find something, depending on whether the type is, you know, a byte or a string or an integer or whatever. And so presently we're getting the default value for string, and effectively that is what we wanting in this example. So I've created a second rather contrived example. Here we have a T-person, which has an ID and other ref and a name. plus a constructor which sets those fields. These should probably be properties with getters and setters, but I'm lazy and it reduces the complexity if we don't have to deal with them. I've also converted our Tdictionary to a TObject dictionary, and we're mapping tperson to tstring. So tperson is our key. And when we create our dictionary, I'm setting the ownsKeys property to true, and which means when we free the dictionary, any keys will get freed at the same time. So this bit of code won't generate any memory leaks. And so we're creating 3 persons, Bob, Alice and Charles, with appropriate keys and other refs, and we're mapping those to info about Bob and so on. Now we want to we've created our dictionary and filled in some data. We now want to pull out some data, and so we might naively think that if we create an identical person, in this case Bob, with the same values, we might be able to look up in our dictionary that person and print out, ideally, info about Bob. This is somewhat not the case, so if we run that, we in fact get an exception, item not found, which is basically failing on this bit of code here. So we have no, this person is not in our dictionary. So this this version of Bob is not the same as this version of Bob, and so they're basically different objects, and that's why our lookup is failing. If we scroll back up to our tperson, we see it descends from TObject, and if I control click on TObject and scroll down a little bit, we see a couple of familiar looking methods, equals and GetHashCode, and they're both virtual. So if we have a look at equals, we see that equality is defined by the memory addresses being the same, so exactly the same object. The GetHashCode on our 32-bit version, which is what we're compiling presently, basically we just are returning the integer version of the memory address of our instance. And on a 64-bit system or executable, we take the low order integer and XOR it with the higher order integer, and we get a fairly unique 32-bit number. There'll only be 4 billion of them, of each of them approximately, but anyway, whereas this one is actually probably quite unique on the system. So what we can do is override our GetHashCode and equals functions, and I'll just press Control-Shift-C to for the class completion, and this time we will go assign obj is, just confirm that as a tperson. Might not actually have to do this, and obj as tperson dot, we'll go with ID equals ID. I probably need to put brackets around that as well. So that's basically we're just doing a comparison and making sure our IDs are the same. And GetHashCode, very simply, we'll just return the ID in this case. So this time, if we run this, we get info about Bob. So just to go over what's happening, when we add this Bob to our dictionary, its location in the dictionary will be determined by the ID, and so this Bob and this Bob will get hashed to the same index in the internal array of the TObject dictionary. And when this person is compared to this person, they'll both have the same IDs, and therefore they will be the same person, and we will get our value info about Bob printing as we see here. So fairly straightforward. Let's now say that our ID is not sufficient to identify a person uniquely. We have to use both the ID and other reference. So I'll just copy, in fact I'll take it from the end. And so we're now having the requirement that our ID and other ref be the same. Now, if we run this now, we do still get info about Bob, but if we have a different, say B12, and this person is actually Bill, and we run this, we get our exception item not found. So this T person is now a different T person from this one. This time things are working out a little bit differently. Although both Bill and Bob hash to the same location in our dictionary, when we go to look up Bill, we will find that there is someone, a person in the expected location, and we'll do a comparison. The IDs will match, but the other refs won't, and therefore the lookup will fail. In fact, we can set a breakpoint there and run that, and we can see that it's ID1, and it's not showing our other ref, but our other ref here is 97, presumably this one's B12. These two aren't not equal, and our lookup fails with an exception. Just one final thing before we move on. We could change our GetHashCode function if say a lot of our persons had IDs that were non-unique, that might degrade the performance of our hash table, and instead we might want to use our other ref as the source of our hash code, and we could XOR that with ID if we were wanting to particularly mess things up. And can run that, we get our item not found, and let's go back and copy that so that we have our Bob back again, and we do indeed find Bob. And just thinking about it, if object is nil, we should probably check for a null object. Otherwise, when we go and grab its ID, it's going to give us a exception. Okay, so that's this bit of the example done. Let's move on. So overriding the equals and GetHashCode has worked great for changing the hash behavior. But what if we don't have an object, but instead have a record? And if I attempt to compile this, we'll get lots of errors, starting with we can't override functions on records. In fact, we can't even use equals or GetHashCode at all. And in fact, I'm going to comment them out because, for now, because they will not work at all. And compile that again. Okay, we don't need to free our person anymore because it's a record, doesn't need freeing. That compiles. We're still going to get a failure in that we get an invalid typecast. Basically, our keys are not classes, and therefore we don't want to own the keys. So I'll just stop that and delete that. In fact, I can delete the brackets as well. And if we run that, now we're going to get item not found in our exception. Back to where we started. Now, in addition, this object dictionary is basically behaving as a dictionary. So if I just edit that and take out the object bit and try compiling that, we are indeed up and running. So the question now becomes, how do we alter the hash behavior? Now, if you remember back, if we go find, let's go to Tdictionary and have a look at the constructors, we'll see that we can specify a equality comparer, an I-equality comparer based on the key. And if I control click on that, it's an interface, but there is a mechanism for constructing one with some anonymous methods, and that's what we're going to end up doing. So I'm going to want to declare an I-equality comparer, so we'll call it a in fact, we just call it a comparer. And it is type T person. Now we also need to add to our uses system.generics.defaults. This one here. If I've spelled that correctly, let's try compiling that. And we'll spell it correctly. Okay. So we want to assign compare something, and if we have a look at our generic, back to system.generic.defaults, we've got this T equality comparer of T, and we have a method called construct, which takes a couple of parameters. So I'll start with that, and in our case we want a T person, and then dot construct. And that takes a couple of parameters, and they are functions, and we're going to need two of them. One is of type T equality comparison, so if we go back, and T equality comparison is a reference to a function with that signature. And they are, of course, of type T person. And a hasher, which is a reference to this function. And we need a comma to separate the parameters. and a semicolon on the end. Now all we need to do is implement these functions with the correct parameter. In fact, we can compile that and test that we have indeed got everything right, and our body might be undefined. No surprises there. Implementing these functions is quite straightforward because we've done it already. Just copy that and throw that in there, and you can say value.otherf.getHash and value.id. So there's our hash function defined, and we want to define equality, which we can also, scrolling the wrong direction again, define in a similar manner. We don't need to worry about that. This is equals right.id and left.otherf equals right.otherf. And hopefully, if I have written that all correctly, we should be able to run that and we get item not found. Because I have not passed in our comparer. And info about Bob. And if we do a similar thing here, change this to our we see that we get our item not found. As before, so we've done both a positive and negative test. Probably not quite sufficient to be fully certain about our application, but that's pretty good. So basically, we have used this construct class procedure or function with these anonymous methods to create an iComparer. You can also manually create an iComparer. Create a class that descends from T-interfaced object and implements iComparer, and then pass that in if you want. And in fact, you can squeeze all of this code into the create method or constructor instead of the parameter directly. It looks a bit horrendous when you do that, so I think this is a reasonable compromise. So I'll leave the other way of manually creating a equality comparer as an exercise to the viewer, and I think that pretty much concludes this session. While this video has been on the very specific topic of altering the hashing behavior of dictionaries, I hope that you've also picked up some more general concepts along the way. You can of course learn more by reading both the online help and the source code itself. If you are interested in learning more about the generic collections library, you can of course purchase my video on this very topic from learndelphi.tv, which not only covers the dictionary class but also TList, TQ, TStack and many others. I'm Alister Christie. Thanks for watching this CodeRage presentation.
Okay, great. Thanks, Alister, for that presentation. Not sure what happened to the audio at the very end there. It got a little quiet. Are you there, Alister?
Okay, can you hear me?
I can hear you.
I believe so. Excellent. So, questions?
So, one question here is what tool are you using to display the key combinations like Control-V down at the bottom?
Okay, that's part of Camtasia. So, the screen recording software I use. There's I think from the edit menu, there's a create keystroke, something or other method, which adds them to the video, which is quite nice in a separate track.
Yeah. Useful.
Yeah.
How large can a Tdictionary get?
I don't know. I presume as much, use as much memory as you've got. So pretty substantial, I would think. And even if the dictionary is huge, you'll still get the constant time performance. So it would still be as snappy as if you only had a few items in the dictionary.
Yeah.
Which is quite awesome.
It is.
I think, yeah.
Is there a video? Do you have a video around binary trees using generics like a TST tree in TurboPower?
No, I've been thinking about making videos on generic sort of computer science topics, which would be quite interesting, but still, a matter of finding time to do it and that kind of thing.
Yeah, absolutely.
Yeah, and of course, binary trees, you've got login performance. So still, you say infinitely slower, I suppose, depending on the size of your tree. The Tdictionary is still going to be way faster.
A lot of positive feedback. Thumbs up for presentation and topic.
Thank you very much.
Is it possible to use operator overloading or operator override with dictionary comparisons?
Operator overloading.
It says operator override. Actually, I misread that.
Override. Okay. I'm not sure what that's referring to, actually.
Yeah.
Use operator. Oh, like using plus to add something to a dictionary, I suppose. It might be the... I don't know, actually. It might be. No, I don't think you can do operator overloading on classes. I think you can only do it on records.
Yeah, that's right. You can only do operator overloading on records, not classes currently.
Yeah. So the answer to that's probably no.
I think you can if you're using the new compiler, the cross-platform compiler.
The next gen, yeah.
The next gen compiler.
Yeah. Yes, because it has the automatic reference counting.
Yep.
Yeah. If people haven't really got into using the generic collections library, I'd seriously encourage it because it does simplify code tremendously, and there's some interesting classes in there. There's stuff for helping with multi-threaded code, and of course there's CList for your standard list, which you can do any kind of type, throw any kind of type in there. I've seen so much code, people abusing the tstring list class for mapping strings to all sorts of things.
Oh yeah, yep. That was the tstring list was the go-to, man. You just throw everything in a tstring list and But now, now with the generic collections, they're so much better, and they got so much more advantages and flexibility and things you can do with them.
Yeah, I mean, on a sorted string list, you get login performance. It uses uses a binary sort if the list is sorted. But if you're using the key value type thing, you're basically getting linear performance because it does a linear search. Mm-hmm. So if you've got 10,000 items, that's actually going to take a measurable amount of time to do that. So the dictionary, the hash table is going to be much faster.
So
yes, indeed.
Question here: can you stream out the dictionary content to a file?
Well, you can iterate over a dictionary. It supports a for-in loop, so you could reasonably implement it yourself. I mean, the hassle is, if you've got classes and things like that stored in it, you need some mechanism of converting your class to a stream or whatever.
It seems like I ran a dictionary of objects through a JSON serialization, and it serialized it out for me. But you can. I'm pretty sure you can.
So I see a question there regarding big O notation.
Yes, big O.
What is it? So the O stands for order, and basically it says it gives you a rough indication of the performance of your algorithm. So constant time, we say, is order 1. If it's linear, it's order n. So if it takes, trying to explain this in without turning it into a computer science lecture. But basically, it allows you to determine the performance of algorithms with larger numbers of items in them. So your constant time is performance is kind of the best you can get, and then you get things like log n, order n, n log n, n squared. So, for instance, quicksort is, or technically it's order n squared, but the general performance is log n, n log n. Where many other sorting algorithms are n squared. And if you run, there's a little threaded demo which gives you does a visual sorting, and I think it does quicksort, bubble sort, and might be selection sort or something like that. And just the quicksort just is really, really fast in comparison because it performs n log n. Whereas the others are n squared, so it's much finishes a lot quicker.
Yeah, that's it's a really useful concept when you're you're dealing with lists of things and sorting them and looking for items in lists and stuff like that, to be able to consider what the different performances are.
Yeah, I'm sure there's a very a good Wikipedia article explaining it.
I'm sure there is. Okay, so to quantify. Now I'm trying to reduce what you said into an answer I can type.
That'd be a bit of a tricky one. Probably find the Wikipedia article and paste that in.
Yeah, that would have been a good way to go. So Alf has a question, another one about a TST tree. So you can stream anything in the class, even variables. So yeah, I'm not sure if the turbo power. I guess it's in that library's in Git, so it's still available, still being updated or maintained.
Yeah, I've not tried them out actually, but I probably should have a bit of a look.
Yeah, there's a lot of good ones out there. The other one is the D# library. It has a lot of generic collections in it as well. So there's a number of good libraries out there with more.
Yeah, Spring Framework as well.
Yeah, that's what I'm thinking. Spring Framework. Yeah.
Interface to base.
Not D#.
Generic collections.
Okay. Well, that looks like the end of our questions here, unless I've missed something here. Nope, looks like we got them all. So
okay, excellent.
Thank you, Alister, for another great session. And we've got a little time before our last session of the day here. So
okay.
Great.
Well, thank you, everyone, for watching. The video is actually a bit of an extract of my commercial video. And yeah, sort of expanded it a little bit more in this video on the topic of hashing. So
okay.
Yeah.
Great. Well, everybody can go check out. It's at learndelphi.tv to check out the rest of your videos and stuff. So lots of good stuff out there.
Yeah, lots of free stuff as well. So.
Yep, free stuff. Yep, excellent. Great. Well, thank you so much, Alister, and thanks to everybody for joining us.